B.3, smoothness rule. Why we need to learn this topic? The reason is, if you look at the previous two videos, what we did in those two videos, we did this way. We start with a special case, and we find a solution. Then we need to go to the general case, right? Yeah. General, yeah. General case, right? But when we do that, we need to do a lot of work, right? Mathematical induction, a lot of work. And that part is not easy. Think about if later, under the similar situation, do we always do that much work? Many times it's not easy, right? Yeah. So here the idea is we want to go from special to general using some special theorem if the situation is right. Just you apply some theorem. When you apply theorem, you don't need mathematical induction, right? You just apply the theorem directly. Right? So here we can treat this part as a shortcut. There is a shortcut we can take, but the situation must be right. The situation related to that smoothness. The smoothness is different from our usual smoothness. Different. Yeah. So many of you, just based on the word, you understand. So in calculus, we have a smooth curve, right? We talk about smoothness of the curve. Here, it's different. The meaning is different from this. So you should be very careful. Yeah. In my question, I will emphasize that part. I will put the words like smoothness in our algorithm context, not in calculus context. So then you need to use the meaning we will discuss in this video. All right, so let's start. In this problem, let's recall what we did. We start with this formula, but that is for a special case. Then we go to the general case, but we did a lot of work, right? Yeah. Yeah. All right, so here we just want to still from special to general, but in a fast way. A faster way. But the situation must be right. We need to check the condition. Yeah. All right. So now let's look at the condition part. Smoothness rule. The reference in Appendix B. Yeah. Situation. Yeah. I just described the situation. Yeah. Here I do not need to repeat it. Yeah. That is smoothness rule. So let me explain. It is very abstract. So this concept is very abstract. Hope you can follow. It's not easy. So based on my experience, it is pretty hard to follow, to understand smoothness rule. Yeah. All right. Let T of n be an eventually non-decreasing function. Eventually, so from these words, you can understand the meaning. Eventually, non-decreasing, non-decreasing. Eventually, after some line. Yeah. In the next slide, you can see the definition. Yeah. But the meaning, straightforward. Yeah. And the f of n be a smooth function. What is a smooth function? Here, you do not see the definition. So in my next slide, I will give you the definition of the smooth function. Here, so we need to hold a little bit. Yeah. Then, if T of n belongs to f of n for values of n that are power of b with b greater or equal to 2. So you can see in our situation, we have that. So our b equals 2 here. But you can see p could be more general. 2, 3, 4, more general. Yeah. All right. Then the conclusion. Yeah. Conclusion. T of n belongs to big theta of f of n for general n. General n means not necessary power of b. Okay? So here you can see the condition T of n belongs to that category, but power of b. Conclusion, T of n belongs to the same category, but for general n. That's the same thing we need in our example problem 10. Yeah. And here, the key condition, f of n is a smooth function. You need to check f of n is a smooth function. All right. The definition, next slide, we will see it. Yeah. All right. Yeah, so here, I put a smoothness rule here, non-decreasing function, I put a definition here. Yeah. The definition, although I put a lot of words here, but the meaning is very simple. Yeah. After some n0 integer, some line, after you pass that, then non-decreasing. Yeah, that's simple. Yeah. The key part, smooth function. I haven't given you the definition of smooth function. That's the key part. Yeah. First, example for non-decreasing function. Our function, floor function, log base 2 of n, it is eventually non-decreasing function. Okay? Yeah. Yeah. You know, non-decreasing eventually. Yeah. Smooth function definition here. Yeah. So that's the main part. Yeah. What is a smooth function? Let f of n be a non-negative function defined on a set of natural numbers. Yeah. Yeah. F of n is called smooth if it is eventually non-decreasing. This part is easy to check. Eventually non-decreasing, but next part, critical. So what's the next part? And f of 2n belongs to big theta of f of n. This is the main condition of the smooth function. You need to check this condition, main condition of the smooth function. All right, example. Yeah. So let me give a simple example. Yeah, log base 2 of n floor function is smooth. Why is smooth? Let's check f of 2n. What is f of 2n? Yeah, f of 2n, it is this, right? Yeah, pull that one out of the floor brackets. Yeah. Yeah, because this is a small constant number, right? Yeah, so we can get it is in the big theta of, yeah. Actually this floor can be gone, right? Yeah, difference is very small. Yeah, log base 2 of n. Yeah, all right. But you can see this is a smooth function easily. But can you imagine some function is not smooth? Here, I like to give you a non-smooth function example, right? Yeah, not smooth or non. Yeah, what is a? Can you imagine some non-smooth function here? Yeah. Let me give a simple example. Yeah. Look at this example. f of n equals 2 to the nth power. How about that? 2 to the nth power. Yeah, definitely you will see f of 2n. What's that? F of 2n, 2 to the 2n. Okay? Or 4 to the n. Right? Definitely you cannot say it belongs to big theta of 2n, right? You cannot say that. Too big. You cannot say that, right? So this is not a smooth or non-smooth function. You can see this kind of example. All right, yeah. So let me finish our video B.3 here. Yeah. The conclusion you will know if you check, by the smoothness rule, you can do that shortcut. Remember that shortcut. You do not need a lot of mathematical work. Yeah. All right, so let's stop here. Yeah.